Okay, tides. Tides are interesting. Tides are really kind of neat, actually. The way to explain tides, it all has to do with gravity. And everything is gravitationally attracted to everything else. Okay? The moon is attracted to the Earth, which is why it doesn't drift off into space. The Earth is actually attracted to the moon, so the two of them are kind of dancing together. That's what Newton's third law says, that everything, anytime there's one force acting on something, the same force, or what's called a reaction force, is acting on something else. Which means, if I'm pulling you on a rope, you're also feeling the pull. Okay, you're feeling the pull, I'm feeling the pull, we're both feeling the pull. So, same with gravity. The Earth is pulling the moon is also pulling the Earth. The sun is pulling us both, and the sun is orbiting the galaxy, and so everything is bound by gravity. One of the neat things about gravity is that its strength doesn't decrease linearly with distance. Okay? It decreases with the square of the distance, or it's inversely proportional. The strength is inversely proportional to the square of the distance. All very mathematical for those of you who like high school algebra. But basically what it means is, if something is twice as far away, the gravity is actually 4 times as weak. Okay? Or if something is twice as close, the gravity is 4 times as strong. So if we look at the gravitational force of the moon on the Earth, here's the Earth. And so let's think of the moon acting on the Earth. Okay? But the Earth is not a single point in space. The Earth is kind of big and chunky. So the Earth has the Earth, but it also has stuff on the close side and stuff on the far side. And because the gravity changes with distance, the stuff on the close side feels a stronger pull than the stuff than the Earth, and the stuff on the far side feels a weaker pull than the Earth. Okay? So if I use some little scale arrows here to represent that, the closest side to the moon experiences the greatest pull of gravity, the greatest tug. Then the far side experiences the weakest tug. So as a result, what happens is stuff on the side of the Earth closest to the moon gets pulled towards the moon. Okay, the gravity of the moon is actually acting on it to pull this stuff more than it's pulling the rest of the Earth. And it's pulling the rest of the Earth more than it's pulling this stuff. Okay? So this stuff is kind of leading ahead, and this stuff is lagging behind, and as a result we get this kind of double bulge. Okay? So there is a bulge pointing towards the moon, and a bulge pointing away from the moon. Okay? Which is why tides occur twice a day, high tide, low tide, high tide twice a day, low tide twice a day. Okay? And not just once a day. So it's not just the side that's closest to the moon, it's the sides both closest and farthest from the moon that experience these tides.
So that's why the sea level.
And that's why the sea level goes up and down. And it's not just the sea level. Okay? The ground we stand on shifts by something on the order of 20 centimeters a day due to tides. One of the things, and the way I found out about this, I was reading an article on the Large Hadron Collider at CERN. And when they were building this thing, they had to take into consideration the fact that the whole thing shifts by 20 centimeters up and down twice a day. Okay? You don't tend to feel it because it's slow. And you're not really seeing it with respect to anything because there's nothing that's not moving. Okay? You can see the water moving because the ground is fixed, right? The ground is stationary, more or less, and you see the water, the ocean tides moving up and down with respect to the Earth. But there's nothing really to compare the Earth to. But if you could, you would see that we're actually moving up and down about 20 centimeters twice a day.
What about the lakes? Lakes don't have tides?
The reason that oceans can really have a tide is because the water can come in from somewhere else and slosh up, right? Since the oceans envelop the whole Earth, there's water that can move in from elsewhere. The lakes are kind of contained. The lakes do move up and down with the Earth, I mean with the dry land that they're on. And some of the larger lakes do experience very minor tides. Lake Superior does experience a few centimeters of tidal force. Usually it's counteracted by wind, which has a much greater force on it, but yes. If there was a way for the water to come whooshing in from somewhere else, then the lakes would experience a greater tide. Okay, but wait, it gets better, because there's one thing I've left out. Okay? Okay, the moon is orbiting the Earth, but the Earth is also rotating. Okay? So as the Earth rotates, it's going to kind of drag that bulge a little bit with it. Okay? So that the bulge, as we see from the surface of the Earth, the tidal bulge actually precedes the position of the moon. Okay? So we see the moon rising, but the bulge, the tidal bulge, comes ahead of the moon because the Earth is kind of pulling it out of the way. It's a little bit weird. This has a couple of additional effects, okay, so that again, this is the scale is exaggerated, but because this tidal bulge is not in line with the moon, it's offset a little bit, okay, the angle of the sort of the gravitational attraction between that bulge and the moon is not a straight line. So there is a little teeny tiny component of force in this direction. And how many of you did high school physics? Okay? Components of force, right? Vector components. There's a little tiny bit of force in this direction, okay? Which is opposite to the direction of rotation of the Earth. So there's a tiny bit of drag on the Earth. But likewise, that force, okay, the force on the moon, because the moon's being pulled towards the Earth the same way, is going to be in the opposite direction. It's going to be towards its direction of motion. So while the Earth is experiencing a little bit of drag, the moon is experiencing a pull. Okay? It's experiencing a boost. As a result, the moon is gaining orbital energy, and it's moving farther away. The opposite result is that the Earth is slowing down. And the rate is 1 second every 40,000 years, which is nothing to worry about. But we have fossils of clamshells. The clamshells are a little bit like tree rings. You can cut them open, you can stick them in an electron microscope, and you can count the rings, and you can use that to date them, but the rings are daily. And so we can use these things to determine that back in, I'm thinking it was a Carboniferous, though it may have been an Ordovician clam that was measured that the Earth had something like 408 days during that time. So the Earth is slowing down and the moon is speeding up and getting farther away.
What happens when the moon is not in our orbit anymore?
Well, by that time we will have more to worry about from the sun, because the sun will have puffed up into a red giant and will be encroaching on our orbit. So we won't care so much. but should we happen to still be around, what we'd see is the moon would get farther and farther away, and eventually it would drift off and become its own thing. Now, whether it would become an orbital body that was sort of in resonance with the Earth, you know, there's other factors to take into consideration. But
so if the Earth is slowing down 1 second every 40,000 years, how far away is it heading every year? Minutes or?
it's centimeters.
Centimeters every year?
I don't know off the top of my head. Sean?
I can in the observer's handbook, I'm not.
Okay.
In the observer's handbook, I'm not totally sure. I'll get back to you.
All right. I know that they do experiments on a regular basis bouncing laser beams off the moon. And they use that to estimate the difference on a yearly basis. And they can get fairly accurate. It frightens me how accurate some of these.
Maybe it's 4 inches every 10,000 years or something.
It's something like that. I mean, actually, I think it's a little bit more than that. I think it's on the order of a centimeter a year, or 2 centimeters a year. I mean, I think the distance is detectable. All
The
right.
moon is receding about 3.8 centimeters per year.
There we go.
Wow.
Excellent. Thank you, Observer's Handbook. You don't actually need me here. You can find this on the book. Anyway.